crucible, and that's what's containing our glass. Now, gathering it out on the end of a pipe like this, it's kind of like trying to get honey out of a honey jar with a dipping stick. It's the same viscosity at that temp. That's what allows us to gather it. So he shapes these centers. Now he's going to form a small starter bubble. Watch closely. This is very subtle. Right there. Did everybody catch that? That's glass blowing. Thank you very much for coming to our demonstration. He did a great job with that, didn't he?
Thank you.
Bad joke. I know that one doesn't go over so well sometimes. But that's the starting point, and that's just how everything begins in glass blowing. Now, this is enough material to make something very small. Drinking glass, an ornament, a little wine goblet, something of that nature. What he's going to do next is simply allow this to cool. When we say cool, that means rigid. Now, rigid glass here is 1,000 degrees. So I know it's not cold to touch, but that's cold in terms of working the material. But once it's rigid and stable, I'll come back over to the furnace, dip that back into that pot of glass. You're going to see him turn to gather up more. So because of that viscosity, there's a limit to how much we can gather at one time. So we make a starter bubble. Now we have more surface area to gather on. The next time, we'll get about 3 times the quantity of glass. So he speeds up the cooling with compressed air or just hanging out, allowing air temperature to do it. But once that bubble hits its rigid state, it's good to go back in the furnace. If you rush it, that bubble is still soft. It'll collapse in on you when you gather it. So you can see these very smooth rotations in one direction, and then he starts to drop the back end of the pipe down to go level, and that really kind of catches that gather of glass. Now, when you watch somebody that's been doing this for a while, it's pretty deceiving. It tends to look a little too effortless and easy, but that is not the case. When you first learn how to gather glass, it's very difficult to control. It takes a good amount of muscle memory and all that dexterity in your hands to turn properly, because if you don't, it really just wants to drip right to the floor. We get a lot of questions. What's the first thing you learn how to make? That is generally the first thing you learn how to make. But Tony's shaping and centering with another one of these blocks. These are wooden scoops. Well, they look like scoops. It's just a wooden tool. It's been soaked in tap water, and they're made from fruit woods typically, which burn slow and clean. They also burn away very smoothly, very evenly, due to their grain structure. So we can use it for a long, long time. Now you might be surprised by this one that he just squirt water on. What's this tool made of? Anybody know?
Asbestos.
Newspaper. Yeah, a few people said it. Folded up layers and layers of newspaper is a wonderful tool in glass blowing. I wish I knew who the first person to create this and use it in a studio was. I don't. Ever since I've been blowing glass, this has just always been a thing. But it doesn't last very long, not because it's getting burned. Once you burn that carbon layer on there, it doesn't really burn so much anymore. It's because it has to stay wet. Wet paper after doing this, about a week or two, it's done. Cracks and falls apart. But it's a really useful tool getting our hands comfortably close to shaping the glass. Now the main resource for what we do is heat. The heat is what allows the glass to be inflated, to shape it, to do anything with it, to form it. So as it's losing heat, it's stiffening, it's hardening. This is a secondary oven used for resoftening, and this one is running at about 2,200 Fahrenheit. Who's asking themselves right now how we get a camera inside that oven? It's a great question. It's a very good one. The camera is safely mounted behind it. The key here is the window the camera looks through. Has anybody heard of fused silica? I guarantee we've all used it here today. Fused silica, it's a very high temperature resistant glass, but it's also optically pure, so it's used in optical fiber technology. So if you've sent a text message, if you've opened up an app on your phone, you have used that type of glass. That's what brings us high-speed internet worldwide. But you'd have to heat that little window, furthermore that furnace, far above 3,000 degrees to do anything to it. So the camera safely looks through it, giving us that shot. So Tony's dipping down into one of the most commonly used molds we have on campus. It's called an optic mold. It's made from aluminum. I bet I can grab a hold of that. Now, it warms up a little bit, but it's nothing too hot because he's only in there for a few seconds. It's like a nice hand warmer now. These are not designed to give you shape, just patterns. And you can see a variety of pieces that have that ridge pattern. Some of them are even twisted. So we dip into the mold to give us that texture, and then the shape is still entirely up to Tony. Now, he's also attached a secondary blowing tool. So the traditional methods of blowing glass, put your mouth in the pipe, blow through with your breath. That's how glass blowing has been done for close to 2,000 years. Well, almost 4 years ago, when COVID-19 hit, the pandemic started, our staff were working, but we had masks on, so we couldn't use that option. So we needed a way to blow glass during that time, and this is what we put in place. That foot pedal, when he presses it, lets regulated air pressure through, and you might be surprised to know that it's set to about 1 psi. If you're not familiar with that, you hold a candle right here, blow it out, that's probably about 3 pounds of pressure. We're using a third of that to blow glass. Doesn't take much. I set that system all the way up to 45 pounds when we first put it. I just wanted to see what it would do. I took a gather glass, popped. Sorry for the sound effects there. But it's very, very important that we're careful when you use compressed air because you can easily overdo it. The fire you see coming off from this tool that he was just using is beeswax. We put wax on the blades of our jacks, the name of the tool, to allow them to glide when you're shaping glass. So a little bit of wax gives us that fire, just a little bit more theatric. You want a solid foot on there, you said? You're gonna spool this on or drop it on? Drop it, great. You got it. But what he did with those jacks, he squeezed them over the bubble and he constricted the glass. He formed a spot where we're gonna break it free. Now that time's gonna come here pretty soon, but first, we'll add a little bit of material for the base or a foot for this bowl. So there's a couple ways we could do that. Tony said he wants to drip it on, so this would be a nice shot of that fluidity. I get that gather right above the bubble, cuts free. Take a seat, shape it up. This is also a really good example of the temperature difference, right? So he's let the bubble drop to that rigid state, so it's not really glowing anymore. But that fresh gather, you can see that bright, bright yellow tint to it. It is very, very hot, very soft. So I'll give him a hand here. He's gonna squeeze the blades into the very middle of that gather we added. And I press pretty generously on the very bottom side to flatten it off. But you can see just how useful those jacks really are. Very, very useful tool. And once he's ready, I'll start up our handle. He gives me a nod of the head, that's my cue. I'm gonna make a handle we call a punty. And this is a very common thing to do in glass blowing. You start off on a blowpipe, you inflate the volume of the vessel, do a little bit of shaping, create the bottom first, and then flip the piece around. So we're gonna attach this to the foot, and once it's in place, it'll break the bubble free from the pipe. Now we want this to stick, but only temporarily. We're gonna set this up so that it will break free when we're done. A lot of that has to do with what I'm doing. Get a little gather of glass, get it to the right shape, and I'm also gonna bring this at just the right temperature. Not too hot, but not too cold either. If it's too cold, it doesn't actually stick to the piece properly. So it's gotta be just right. I felt like it was pretty good contact. I go loose-handed for all these moves. I let Tony grab a hold with whatever tool, tweezers in this case, and do all the steering. I'm good, anytime you're ready. A little bit of thermal shock can be utilized. Drops of water hit that line, quick cracks form, and a swift tap to do it. Let's give him a big round of applause for that. That was very smooth. That's one of the harder parts of the process to really get the right feel for. Now, soda lime glass, the type that we're working, is very prone to thermal shock. We just saw it under control. A little bit of water hitting that constriction creates tiny stress cracks. But let's say you go into that transfer and the piece is a little too cold, those cracks travel, the whole thing falls apart on you. So you gotta be really cautious to keep the temperatures just right. And you learn those temperatures, you get a good timing sense with years of doing it. Got a question?
Why don't you wear
gloves?
Yeah.
Yep. We don't wear gloves generally because we don't need them. These pipes are made from stainless steel, which is not a good conductor of heat. So you can see the really shiny section. It starts to tarnish a bit right here. Now this, we haven't actually put this into a furnace yet, so I can kind of grab down here. These are preheated, so that's about 1,000 degrees, but I can hold on right here, no problem. So as long as you don't grab too low, you're fine without gloves. Now if you put a glove on, it really hinders the dexterity that you can have. So using the hand tools and turning the pipes, we really use our fingertips too for a lot of this. So you can put a glove on, but it's gonna really kind of hinder that.
Why didn't it burn the floor there when you dropped the hot glass?
The floor is actually metal. Yep, the floor is metal. So we have a pan right here that if we're cutting glass, I'm not sure if Tony will cut any of this, We have a pan it drops into, but the floor is aluminum. Now, we wouldn't want to drip like a giant gather glass on the floor because that could warp and distort it, but that little bit was nothing.
Okay.
I have been in hot shops with wooden floors, and that's a little scary to me. I don't know why you'd want to do that. I've also worked in hot shops where people painted their concrete, and that's also really bad because then you get burning paint, and that doesn't smell so nice. Are there any other questions while we're at it? Okay. Well, you can see Tony has refocused the heat. He's got the top edge nice and soft. He is going to trim around the opening. Before we trim, sometimes you see us do this. We pinch and pull. We call that tweezing. So he tweezes the lip, which stretches it thinner, and then he goes in there and quickly cuts away with those shears. Very easy to cut through glass, but you gotta work fast to do so. When something's thin like that, you have seconds to do that because it does stiffen up very quickly. Okay, let's see. There's a few trims down here, but I can still see the one that has a little glow to it. So that has no more movement. But remember, I said we call this cold glass, right? A little bit of water squirted on it. You can see it's anything but cold. So that does two things. It shows you how quickly the glass shocks from that water hitting it. So we're seeing thermal shock, all those tiny fractures that form. But you can also see that it is still quite hot. So ultimately, to avoid thermal shock, what we need to do with our glass is slowly cool it. And we have ovens that are programmed to do that. The oven up here is right behind this, the bench. And if you can read that, it's set to about 960 degrees, give or take. But we put everything in there. When we're done today, we run the program on that computer. So it's hooked to a thermostat, and it's programmed to slowly reduce until it hits about room temperature. If you don't do that, that glass will crack, it will break. Pieces like this take about 8 hours. The thicker something is, the longer that slow cooling ramp needs to be. So it's not a cooler per se, it's not a refrigerator. Some people are confused by that. It is an oven that just drops in temperature gradually. All right, Tony's making quick work of this, and he could certainly stop right there. That's a lovely form. Nice straight-sided bowl with good optics and a foot. But I think he's going to open this up quite a bit more. Are you going for it this time? And with a few sets of doors on this reheating chamber, he's going to get a lot of heat in here. See how slow he's turning too? He can read the softness in the glass by how it starts to move. So the hotter and softer it gets, it starts to ruffle a little bit. So he's turning very slow, but at the right moment picks up that speed using rotational force, gives him all the room he needs, opens it up nice and wide, and wait for it, hangs it to the ground, and lets it ruffle on itself. What do you guys think?
Oh, that's cool.
Nicely done, Tony. Beautiful. Now you can see how quickly that really kind of freezes into shape. Freeze being the wrong term there, but turns rigid enough that it's got its final form. So the next step is to get this quickly off that rod and into the annealing oven. To help it break free, he might stress that connection out. It's a small connection, so it shouldn't take much, but a little bit of water placed strategically on the puntee. Create enough stress. Quick tap does the rest. Let's give him a big round of applause. A beautiful optic bowl. So we'll waste no time. Thank you, sir. And away it goes into our annealing oven for safe and slow cooling. Let's give him another big round of applause, folks. He did a great job of that. Now,